Hey guys, how's it going? Welcome back. We're going to be continuing our discussion on acids and bases today. One of the things that makes the topic of acids and bases a little bit easier for students to understand is the fact that they come into the unit with a little bit of background related to acids and bases. Back when you were in middle school, you probably had a introductory course on physical science in which at some point during that study you got into a discussion of what pH was and talking about acids, bases, and neutral. And one of the things that students have a tendency to have a good understanding about is pH. And a lot of students come into chemistry with an understanding of the reference point on the pH scale being 7, meaning everything 7 is neutral. And so a lot of students have a tendency to associate water with being neutral, in which it is. And then anything below 7 on the pH scale is an acid. A lot of students will inaccurately say 0 to 6 or 0 to 6.9. You don't want to make a frame of a low end and a high end number for acid or base region. Basically, you're going to use 7 as your middle point. That's neutral. Everything less than 7 is an acid. Everything greater than 7 is a base. That's what we have to focus on. But a lot of students don't have an understanding of where those numbers come from. It's not just an arbitrary number. It's not as if somebody just picked their favorite number, which was 7, and said this is going to be neutral and everything less is an acid and everything greater is a base. These numbers are rooted in mathematics that you may or may not have studied yet, depending on what level of math you're in currently at St. Francis. So we're going to get into acids in terms of pH and where the pH numbers come from in terms of two ions. So to begin today, if you remember from our previous studies of acids and bases, we talked about different theories of an acid and a base. We talked about the Arrhenius theory and the Bronsted-Lowry theory. And tables K and L in our reference tables give us a good understanding of what to look for when we're looking for an acid and a base. Acids generally begin with hydrogen, followed by some other nonmetals in their formula. Acetic acid can be written a little bit differently. And then bases, for the most part, contain metals combined with OH. And then there's that oddball ammonia, which is found on table L. And in our study of the different theories of acids and bases, we got an understanding of why ammonia is a base according to the Bronsted-Lowry theory. The fact that it can accept a hydrogen, which when put in water produces the OH minus ion. So when we think of water, so I'm going to take it back one frame here. When we think of water, this is what we think of. We think of water as a liquid substance in which the water molecules are arranged randomly. Remember, that's the term for randomness is entropy. So with not as much entropy as a gas, but with more entropy than a solid. So this is a good illustration of what two molecules in water look like based on their Lewis structures. Remember, according to collision theory, if two molecules collide with proper energy and proper orientation, they will react. And sometimes reactions don't go to completion, they reach equilibrium. So a lot of what we learned about in the previous unit is reappearing as some of the understanding of this unit in acids and bases. So if we take this green water molecule and we collide it with sufficient energy and orientation with this red molecule here, what can potentially happen in water is this can lead to a reaction where we end up with a reaction where this dissociates and breaks apart from one water molecule, resulting in an OH ion that has an extra set of electrons, an extra electron. And the result here is a polyatomic ion with the formula H3O plus that can lead to the production of a hydronium ion. So essentially what can happen in water is a water molecule can react with another water molecule and this can reach equilibrium. So I'm going to put my double arrow here as best I can. Oops, I can do better than that. There we go. And what happens is you get H3O plus and OH minus. Now remember, this is happening in water. Now we know water is a neutral substance. But if you take a look at what's happening in water here, you have the hydronium ion, which if you remember from the most recent POGIL that we did, this is an ion that we found in acids. And we also have the hydroxide ion, which we normally associate in bases. But all of this is happening in water, which is neutral. So how is it possible for water, which is neutral, to have ions that we associate with acids and ions that we associate with bases? How is this happening? Well, this is happening on its own, reaches equilibrium, but when it reaches equilibrium, those two ions that we associate with acids and we associate with bases are found in equal concentrations. So if you remember from here, acids have the H plus and bases have the OH minus. So we have these ions that we associate with acids, and we have these ions which we associate with bases, but it's neutral. So they must be there, but they must be in equal amounts. So if you're following along in your notes, which I hope you are, in our college prep notes, this begins on page 11, Roman numeral number 8, and it's going to continue to page 13. If you're following along in our honors notes, this is going to continue. This is going to be found in Learning Guide 11.4. So we're talking page 10 to page 12. And so what we just discussed here was the beginning of the notes up here, letter A. So to show you like a map, to show you what this looks like, here is a visual representation of water. So over here on the right-hand side, you'll see a sink full of water, and you see the pH meter here is 7.0. And if you look off to the left, you'll see that there is a concentration that's given for the hydronium ions in water and the hydroxide ions in water. And if we look at the concentration of each of those in milliliters, and you see here that there's an equal amount of the hydronium ions that are the red dots and the hydroxide ions, which are the blue dots. So you have an equal amount of hydronium ions in water and hydroxide ions in water. Now you might have thought going into this that water is just water, it's just H2O molecules. And that would have been a good assumption leading up to this because we really didn't talk about equilibrium and we didn't get into collision theory up until the last unit. But what really happens in water is the water molecules collide with one another, they react with one another, and when they self-react, they transfer a hydrogen. So remember, the proton donor is the acid, and they accept a hydrogen, and the proton acceptor is the base. And what that results in is H3O plus and hydroxide ions in equal concentrations, which is molarity, of 1 times 10 to the negative 7. So both of these ions have concentrations of 1 times 10 to the negative 7. Now think about those numbers and how it relates to the pH scale. Again, the pH of a neutral solution, which maybe a lot of you guys recognized, had a pH of 7. So neutral water has a pH of 7. but it has concentrations of both acid ions, hydronium, and hydroxide in equal amounts, 1 times 10 to the negative 7. So notice that there is a relationship between this exponent up here and this pH here. How does that happen? Well, this is rooted in something called logarithms. So I'm going to go to my calculator for a minute so I can show you guys what a logarithm is. Now, some of you guys that are in Algebra 2 Trig might have already been introduced to what a logarithm is. Let me show you what a logarithm is. A logarithm is the opposite of a base 10 power. What does that mean? Well, let's say that I took 10 and I raised it to, let's say, the third power. So 10 times 10 times 10. Now we know that if we take 10 and raise it to the third power, we get 1,000. Now, if I were to take the logarithm, the opposite of this, of 1,000, what I would get is 3. So what this answer tells me is that if I take 10 and I raise it to the third power, I get 1,000. The opposite of that, if I take the logarithm of 1,000, I would get 3. Now the thing is that we're not working with really large numbers. We're working with really small numbers, quite the opposite. For example, let's go back to our numbers over here. So in neutral water, remember it's got a pH of 7, which is neutral. There is water molecules, and there's also these hydronium and hydroxide ions. And if I were to put this number here into my calculator using the logarithm button, so if I take log and I take this number here, 1 times 10 to the negative 7. So 1 times 10 raised to the negative 7 power, and I equal that, it equals negative 7. Now, we don't like working with negatives. But what if we took the negative of that? So if I took the negative of negative 7, I get 7. Now notice that the number that I get here is the pH. That's where pHs come from. pHs are based in logarithms of the concentration of this ion. So if I go back to my notes, if you're looking at my screen, those are our new COVID kitties that we got the other day. So every aqueous solution, not just acids and bases, contain both hydronium and hydroxide ions. In fact, what I'm going to do here is I'm going to open up these notes so that I can show you what it looks like filled in. I should have had this open already. I forgot to. I apologize. So as you're watching this on YouTube, This would be a good spot to fast forward a little bit until you see the word pop up again. My apologies, guys. All right. All right. So in pure water, what you have is both ions in equal amounts at 1 times 10 to the negative 7th molar. And that's what we saw here in this illustration. Okay, so we have an equal amount of red dots, equal amount of blue dots in proportion. They are equal with a concentration of 1 times 10 to the negative 7. Now, we learned in the previous unit using Le Chatelier's principle that if we increase one ion, the other one goes down. For example, in this reaction, if I increase the amount of hydronium, if this goes up, this goes down. If this goes down, this goes up. Let me show you an example. So let's say to this, so let's empty out some water. Yep, come on. All right, so if I empty out some water, and let's say to this I add an acid. Let's say I add something like orange juice. So if I add some orange juice to this, which is an acid, notice that as the hydronium concentration went up to a factor of times 10 to the negative 4th, the concentration of the base ions, hydroxide, goes down to a factor of 10 times 10 to the negative 11th power. Let's say I add a base to this. A common base would be something like drain cleaner. So if I add drain cleaner to this, now all of a sudden, the drain cleaner makes the concentration of the base ions go way up to 1 times 10 to the negative 1st, and the concentration of the acid ions go all the way down to 10 to the negative 13. So as one goes up, the other goes down. So let's get rid of this drain cleaner. And let's start over with some water. Now, in every aqueous solution, you can have one of three possibilities. Either there's going to be more hydrogen than hydroxide, that makes it an acid, more hydroxide than hydrogen, that makes it a base, or there's going to be equal amounts, which is neutral. Again, going back to here, when they're in equal amounts, the pH is 7, and it's neutral. Something like, let's say, coffee. As one goes up, hydronium, the other goes down. Hydroxide goes down. If I were to replace this with a base, let's say hand soap. the concentration of the hydronium go way down to 10 to the negative 10th power. The hydroxide go up to 10 to the negative 4th. So where does the pH of these solutions come from? The pH comes from taking the negative logarithm of the hydrogen concentration. Let me show you an example on here. All right, so let's say we were to add to our container vomit. Now think about what happens when you throw up. When you throw up, you get that burning sensation in your throat. The reason for that burning sensation in your throat is because it's an acid. Look at the pH, it's a 2. And look at all the red dots that are in here, but yet look at the one blue dot. So there is some blue dot in there. In fact, if I were to add more, so I'm just filling this with vomit. You can see there's not too many blue dots. There's another blue dot. So they're there, but they're in small amounts. Now, if I take a look at these two numbers right here, the hydronium and the hydroxide, notice that the pH of 2 is also the negative of what this exponent is raised to. So if I go to my calculator, if I take that number and I take the negative logarithm of it, so let's take the logarithm of 1 times 10 raised to the negative 2, I get an answer of negative 2, but if I take the negative of that, it gives me 2, which is what my pH is. And even bases are based on this concentration over here. Let's empty this out. And let's fill it with a base. Let's fill it with spit. Nah, don't like spit, just because it's not a nice round number. So there's not too many bases to choose from here, guys. So, blood is just slightly basic. Go back to hand soap. All right, so using hand soap, let's fill it with some more hand soap. And again, if you take a look at the hand soap, notice all the blue dots in there, and notice the sporadic red dots, 1, 2, 3 of them. So they're there, they're just in low amounts. But if I look at the two concentrations, it doesn't matter that there's more hydroxide when I'm calculating the pH. The only thing that the concentration of the hydroxide tells me is that because there's more OH minus than H3O plus, that just tells me it's a base. Now, if I take this number over here, 1 times 10 to the negative 10th, which is my concentration of hydronium, if I take that and I put it into my calculator, so if I take the logarithm of 1 times 10 raised to the negative 10th, I get negative 10. So if I take the negative of that, it gives me 10. So this answer in my calculator is consistent with the pH up here. So that's how the pH is calculated. You take this concentration of hydronium that are in the solution, and you take the logarithm, the negative logarithm of that. Take a look at orange juice. 3.2 times 10 to the negative 4. So if I take the logarithm, 3.2 times 10 raised to the negative 4th power, and I it equals negative 3.49, but if I take the negative of that, I get 3.49. Rounded off, that's 3.5. So that's my pH. Now, the pHs that we use in acid-base chemistry are always going to be whole numbers. So it's easier to use an example like the vomit. So if I fill this with vomit, even though I'm adding more vomit to the container, it doesn't change the pH and it doesn't change these concentrations. So if I take this concentration of hydronium that's found in the vomit, 1 times 10 to the negative 2, and I put it into my calculator, So logarithm 1 times 10 raised to the negative 2 power, I get negative 2. Now if I take the negative of that, I get 2, my pH that's found up here. So all you got to do is just take this exponent in the hydronium here and take the negative of that, and that's your pH. So the negative of negative 2 is 2. The negative of negative 1 is 1. The negative of negative 10 is a pH of 10. The negative of negative 13 is a pH of 13. So that's how you calculate the pH. Now, the last thing we have to talk about is when you're comparing two solutions. So let's say I'm comparing my drain cleaner to my hand soap. So look at the pHs on the screen. The drain cleaner is 13. The hand soap is 10. So which of these two is more basic? A pH of 13 or a pH of 10? Well, remember that a pH of 7 is neutral. So the further from 7 it is, the more basic, and the further from 7, the more acidic. So the drain cleaner with a pH of 13 is more basic than a pH of 10. But how much more basic is it? Well, if we take those two numbers, 13, and subtract 10, I get 3. That doesn't mean it's 3 times more basic. We have to take 10 and raise it to the third power. It's 1,000 times more basic. 1,000 times more basic. Let me give you another example. Let's look at two acids. Let's look at the battery acid. So the battery acid has a pH of 1. And let's look at the orange juice. Let me find another one. Coffee. All right. So let's compare those two. So the battery acid has a pH of 1. And the coffee has a pH of 5. So which one is more acidic? pH of 1 or pH of 5? Well, we know the further from 7, the more acidic it is. So the battery acid is more acidic than the coffee, but they're both acids because they're less than 7. So how much more acidic is the pH of 1 than the pH of 5? Well, if we go into our calculator and we subtract 5 minus 1, that equals 4. So if we take 10 and raise it to the fourth power, 10 times 10 times 10 times 10 times 10, we get 10,000. So the one with a pH of 1 is 10,000 times more acidic than the one with a pH of 5. And the one with a pH of 5 compared to water, water. So water is 7, coffee is 5. So if I take 7 subtract 5, I get 2. So if I raise 10 to the second power, I get 100. So that means that coffee with a pH of 5 is 100 times more acidic than water with a pH of 7. So for example, if the pH changes from 4 to 2, that means it becomes 100 times more acidic. If the pH changes from 3 to 6, it becomes 1,000 times less acidic. So that's how you look at pHs and determine which one's more acidic, which one's less acidic, and how much more acidic it is. You take the two pHs, subtract them, and you raise 10 to that power. 6 minus 3 is 3. 10 to the third power is 1,000. 4 minus 2 is 2. 10 to the second power is 100. So I gave you a little bit of a pH scale there and a little bit of a summary table here at the end of this topic. As one goes up, the other goes down. And notice that the pH is always equal to the negative of this exponent here. The pH here is always equal to the negative of the exponent here. And you can see that this exponent plus this exponent always equals negative 14. So these numbers are not just arbitrary, they're actually rooted in mathematics. Okay, we got one more little topic left in this unit on acid-base indicators. Hope this was helpful, guys. Take care.